What would it take to create not just one, but an entire network of O'Neill cylinders, each a self-sustaining world in space? In my last video, I stated that the O'Neill cylinder had an 8 km diameter, which, retrospectively, was way too ambitious. The error occurred right at the start of my research and continued up to the audio recording, where I noticed my mistake. At this dimension, conventional materials like aluminium, steel, and even titanium fail due to tensile stress because of size, weight, and centrifugal forces. All my other consecutive work was based on the surface area change. Nevertheless, to stay true to science, I retroactively corrected all mistakes in my work, and the previous video doesn't need to be obsolete. Carbon fiber can even work on a larger scale. It is just not the ideal material for a precursor to space colonization. Starting with the titanium alloy for the first O'Neill cylinder is a pragmatic choice. It minimizes upfront complexity, uses proven materials, and sets the stage for carbon fiber manufacturing in space. This phased approach ensures a balance between immediate feasibility and long-term scalability, making it a realistic path for humanity's first step towards constructing space megastructures. Our station will be located at the L5 Lagrange point, serving as both a springboard for future outposts and a hub for independent living. The habitat will maintain 1 g of gravity, supporting sustainable life and exploration. The negative aspects of space require Earth-bound life to have a safe haven from both radiation and zero gravity, which smaller space stations might not support. Further questions will be answered in the next chapters. When it comes to the size of O'Neill cylinders, several factors justify why the chosen dimensions strike the right balance. Smaller cylinders can affect humans and structural materials due to higher rotational speeds. This exacerbates the Coriolis effect, leading to dizziness or disorientation, especially near areas with extreme gravitational variance. Larger cylinders provide psychological benefits, offering the illusion of an open sky and reducing claustrophobia. An artificial horizon within the cylinder further mitigates this effect. The feasibility of a 6 km O'Neill cylinder represents a compromise between size and cost. Modern materials can theoretically support larger diameters, such as up to 10 or even 12 kilometers, but construction and material costs increase exponentially. The length can be modular, 12 kilometers rather on the small end. As previously stated in popular science fiction, 24 or 36 kilometers is nothing out of the ordinary. In principle, cylinders could extend indefinitely in length. However, torsion, vibration, and bending forces impose practical limitations. Torsion refers to the twisting forces that arise from uneven mass distribution or rotational stresses. Nevertheless, in our design, this allows for extensions of an additional 12 kilometers at a time if expansion is ever needed. The selected dimensions support an initial population of around 100,000 inhabitants, with room to scale upwards as infrastructure grows. A cylinder of this size provides approximately 225 square kilometers of usable surface area, allocated for urban, agricultural, and industrial purposes. A cylinder with a 3 km radius optimizes the balance between artificial gravity, human comfort, structural feasibility, and scalability. Larger radii introduce exponential challenges, while smaller ones compromise usability and comfort. This size is ideal for creating a sustainable habitat for long-term space colonization. Constructing an O'Neill cylinder is not just a question of engineering. It's a logistical challenge on an unprecedented scale. Earth's surface is an unsuitable launch site for such massive structures due to gravity and atmospheric resistance, which increases costs exponentially. Instead, construction takes place in space. The raw materials come from two key sources, the Moon and asteroids. The Moon provides a near-Earth supply of regolith, a byproduct of mining operations, which is essential for radiation shielding. Mining on the Moon also yields ores that can be processed into steel, aluminium, titanium, and silicates. Titanium, found in the form of ilmenite within the lunar regolith, can be mined and refined for use in high-strength structural components. Asteroids, on the other hand, are rich in metals like nickel and iron, which can be refined and used in various construction elements. These materials are extracted using advanced mining systems. On the Moon, either robotic or conventional miners excavate regolith, which is then transported into space, most likely with conventional freighters, though mass drivers, essentially electromagnetic catapults, could also be considered. Asteroid mining involves autonomous or semi-autonomous drones, equipped with lasers and excavators that break down the asteroid into manageable pieces for processing. The construction itself takes place at Lagrange point 5, a stable region in space where the gravitational force of Earth and the Moon balance out. Modular components are fabricated using 3D printing technology, enabling precision and scalability. These modules are then assembled in orbit, piece by piece, with the help of robotic arms and autonomous systems. Even in space, construction is not without its challenges. Workers must contend with extreme temperatures, radiation, and the need for constant resupply. Overcoming these obstacles require a combination of human ingenuity and robotic assistance. Once the structure is complete, the challenge shifts to making it livable. The O'Neill cylinder must function as a self-sustaining ecosystem, where every resource is recycled and reused. The air inside the cylinder doesn't come from Earth. It's generated by plants and carefully monitored systems. Advanced bioreactors and algae tanks play a crucial role, converting carbon dioxide into oxygen while producing biomass for other uses. These systems are supported by chemical scrubbers, which ensures air quality remains stable. Water operates in a closed-loop system. Every drop, from artificial rainwater to wastewater, is captured, filtered, and reused. Reservoirs store excess water, while condensation systems collect moisture from the air, mimicking Earth's natural water cycle. Temperature and humidity are tightly controlled through climate regulation systems. These systems prevent overheating and ensure that conditions remain comfortable, even as the cylinder absorbs energy from the sun. Life support doesn't stop at air and water. Waste recycling turns organic materials into fertilizer, feeding the cylinder's agricultural zones. Meanwhile, inorganic waste is processed into raw materials for repairs and manufacturing, closing the loop on resource use. None of these systems would function without proper radiation shielding. The total thickness of the structure is slightly over 1 meter. Water serves as shielding against neutrons and secondary radiation, while regolith blocks cosmic rays and gamma radiation. The water also functions as a temperature sink, storing and redistributing excess energy. This is critical, as the only way to dissipate heat in space is through radiation. This refers to heat transfer, not the cosmic radiation mentioned earlier, and contrasts with the other modes of heat transmissions. Conduction and convection. Approximately 15% of the outer surface of the O'Neill cylinder is covered with radiator panels to dissipate heat into space. Energy is the lifeblood of an O'Neill cylinder, powering everything from climate control systems to agricultural zones, lighting, and industrial processes. Solar energy serves as the primary source, harnessed by extensive arrays of mirrors and solar panels. These mirrors, positioned outside the cylinder, focus sunlight onto its surface, where up to 70% of the outer structure is covered in solar cells. This vast area provides an output of approximately 16 gigawatts, comfortably exceeding the cylinder's estimated peak energy requirement of 9 gigawatts. The light collected by the mirrors also plays a dual role, simulating natural daylight for the interior environment. This creates a sense of normalcy for inhabitants, while ensuring optimal conditions for plant growth in the agricultural zones. The combination of advanced solar panels and reflective systems makes solar energy the cornerstone of the cylinder's power infrastructure at Earth's L5 point, where sunlight is abundant. However, the reliance on solar power becomes less practical as habitats move farther away from the Sun. For example, at Jupiter's orbit, solar intensity drops to about 4% of what is available near Earth, severely reducing the efficiency and output of solar panels. In such scenarios, backup power sources like small to medium-sized nuclear reactors become indispensable, not just for redundancy, but as the primary energy supply. These reactors ensure that critical systems remain operational, regardless of distance from the Sun, and they can scale to meet the higher demands of industrial processes or emergencies. Fusion energy, once matured, could also serve as a sustainable and highly efficient alternative for long-term energy needs in the outer solar system, eliminating the limitations of solar power altogether. Until then, nuclear reactors remain the most reliable option for backup and primary power in regions where sunlight is insufficient. The energy distribution network is just as crucial as the power generation itself. Advanced smart grids ensure that electricity flows efficiently across the cylinder, prioritizing life support and critical systems while balancing industrial and residential demands. These grids are equipped with fail-safes to prevent overloads and redistribute power during emergencies, maintaining the delicate equilibrium required for the habitat to thrive. By combining a robust solar energy system with reliable nuclear backup, the O'Neill cylinder achieves an energy infrastructure that is both sustainable and adaptable, capable of supporting human life in diverse locations across the solar system. In the heart of the O'Neill cylinder, agriculture thrives as a harmonious blend of tradition and advanced technology, designed to sustain its population of 100,000 and serve as a vital export hub for the solar system. Covering 30% of the cylinder's vast interior, this agricultural domain is a testament to human ingenuity and adaptability in space. The agricultural expanse is thoughtfully subdivided to balance efficiency, biodiversity, and sustainability. Conventional farming dominates 40% of this area, with golden fields of wheat, vibrant patches of vegetables, and rows of rice stretches along the gently curving interior walls. These crops, grown under carefully managed artificial sunlight, provide staple food for the inhabitants, while producing surplus for trade. Adjacent to these fields, grazing pastures occupy 20% of the agricultural land, where goats, sheep, and cattle roam freely. These animals not only supply meat and dairy, but also play a key role in maintaining the nutrient cycle of the soil. Additionally, chickens are integrated into these systems, providing a steady supply of fresh eggs and poultry. Their coops are strategically placed near the grazing zones, allowing for efficient management and nutrient recycling through composting. Interspersed among these functional areas are lush forests, covering 15% of the agricultural zone. These green oases are home to diverse plant species, fruit-bearing trees, and essential pollinators like bees. The forests serve dual purpose, offering ecological stability and producing valuable fruits and nuts for both local consumption and export. They also provide a serene escape for the cylinder's inhabitants, fostering a connection to nature even in the depths of space. Innovative systems like aquaponics and hydroponics integrate seamlessly into this agricultural ecosystem. Aquaponics, occupying 10% of the space, merges fish farming with crop cultivation in a closed-loop system, producing nutrient-rich fish like tilapia alongside high-yield crops such as tomatoes and peppers. High-stacked hydroponics, though occupying only 15% of the area, stands out for its efficiency. These vertical farming towers, strategically located near population centers, grow leafy greens, herbs, and quick-yield vegetables, maximizing output while minimizing space. The agricultural area is not just a source of sustenance, it's an economic engine. High-value products like dried meats, nutrient-dense grains such as quinoa, aquaponic fish, and eggs are packaged for export, ensuring the cylinder remains an essential node in the solar system's trade network. Advanced logistics systems distribute these goods internally and prepare them for shipment, creating a seamless flow of resources. This balanced approach to agriculture ensures the cylinder not only sustains its inhabitants, but also nurtures its ecosystem and bolsters its position in the broader economy. With every crop harvested, every animal raised, and every shipment sent, the O'Neill cylinder reaffirms the economic viability of a project of such a scale. The O'Neill cylinder is more than a dream. It's a blueprint for humanity's survival and expansion. Its construction represents the best of human ingenuity, from its innovative industries to its self-sustaining ecosystem. But as we look to the stars, we must also look inward. How do we ensure that these habitats are inclusive? That the lessons of Earth's history don't repeat themselves among the stars? In our next video, we'll explore the societal and economic dimensions of the space colonization. What does governance look like in space? How do we build a fair and just society among the stars? And what role will Earth play in this new chapter of human history? The answers are still being written, but one thing is certain: the stars are waiting. All we have to do is reach.